We're going to start now with the synchronous distributed training, as I announced before. So in this session, in more detail, we're going to start with the refresh on stochastic gradient descent. Then we're going to do a lab to refresh a bit and just to remind ourselves of the algorithm. And quickly we will move to the synchronous distributed version that we're going to deal with in the course. We're going to learn what is the ring of reduced algorithm. We're going to introduce Horovod, and then the other, the native solution, the native support for distribution. You will learn it later before lunch with Enrique. So after Horovod, we are going to do the same lab here that we did of stochastic gradient descent. We're going to learn how to convert it to Horovod and play a bit with it. And then just before lunch, we are going to do it with the CNN on MNIST, a very simple example, using both those solutions, Horovod and TF distributed. Okay. So let's say that we have a data, some data. This is very simple data. This is a unidimensional data, and it looks something like a linear model would explain it. So let's say that we want to train a model on this data, and so we select the model what we want. This is a linear model with the parameters m and n, and we select a loss function. This is the things that we need to do the fitting. So in this loss function, if we replace the prediction here, so we have the squares, the sum of the squares of the difference between the predicted values of the model and the data. So we replace here the predictions by the model, and we sum over the x and y. We're going to get a function loss in function of m and n. Okay, and we can plot it. It would be something like this. So here, this is a contour plot. If you see, this is a parabola going outside of the screen. Okay, and in a contour plot, every line, all these lines here, these curves, they are at the same level. No, those are constant. And here, the closest the lines are, the slope is higher, and here it's a bit flatter. So you get something that is very high here, and the end is more flat. Okay, it's a parabola in 3D. Okay, and the value in this direction is the loss, and then you have m and n. Okay, the offset and the bias. Sorry, and the slope, the offset and slope. Okay, so when we want to do the training, in general, we start from a random position. Let's say this one here. That this corresponds to a line that doesn't explain the data. It's just random, and we want to find the minimum in this case, which is this one, that will give us the values in the model that will explain the data. No? This is what we want. So this one we do it in general with a stochastic gradient descent algorithm or other algorithms that comes from it. And how we do it is we have the loss. We evaluate the loss function for a batch of n samples. This is called the forward pass. Then we get the gradients of the loss with respect to the parameters of the model. This is called backpropagation. And then we use this gradient here to update the position in this loss function, loss surface, and we repeat it many times until we arrive to the minimum, until the model converges. Okay, so when we repeat it many times, it looks something like this. We have all the steps here, and here in this case, this plot corresponds to having the batch size equal to the whole training data. And no training data. So there are all variants because the batch size is a parameter that you have to study in your when you set up before setting up your calculations. You can use batch size equal 1, that this is called originally stochastic gradient descent. And then here the path is something like this, very chaotic and oscillates a lot. And in general, most of the cases, what we do is to use a mini batch, which is a batch of size between 1 and the whole data set. No? And we select, we go over different values, 32, 64, 128, whatever. And we find which one gives us the best, the fastest convergence. Okay. And this one gives us a path that is not as flat as this one, continuous as this one, and not so chaotic. It's something in between, depending the size of the mini batch that you use. Okay, so this is pretty much what happens on the gradient descent and the stochastic gradient descent algorithm in its basic form. And now we can move to a lab and play with this, try to reproduce the same figures and refresh a bit how stochastic gradient descent works. Trying to move here. Okay, so we go to this notebook, stochastic gradient descent, SGD, 1 linear regression, stochastic. So we are here, TensorFlow training, stochastic gradient descent, and we open linear regression. Okay? So before, please make sure that when that here you have TF multi-GPU kernel. So if you don't, click and find TF multi-GPU in your list of kernels and select it. And this one will give you the kernel. So I will give you 10 minutes. No. Yeah, 5 minutes I think should be enough. And then we discuss the notebook to play with it. Before I leave you alone, just a small introduction. So here, what we do is we generate some data based on a kind of on linear model. We get this reference slope and offset, the same thing that we had before in the slides. And then we generate random points and we add some noise and we get something like this that we can fit with the linear data. Okay. And then we, from this data, using TF data set from tensor slices, we create a dataset object that we're going to see more in depth in the afternoon. But well, the point here is that you create a dataset object, then we shuffle, we create batches of 100, and we do 150 epochs. We have a linear model that we define it using Keras sequential. To make it linear, we use the same thing of a neural network, but in this case, we put only one weight. There will be only one bias, and the activation is linear. So this will give us a linear model. We select stochastic gradient descent as an algorithm. We compile the model, and so it's pretty usual stuff. I said this part. This part is a bit. It's not really part of the training. We create here this class train history. It's just to use it as a callback to store all the values of the slope and the offset and the loss during the training, so we can do plots afterwards. So this one, the only thing that it does is after every batch ends, it will append the current values of the model variables of the M and N, no, the offset and the slope, and we do the same for the loss. We do like this, and then we pass this history callback as a callback in model fit. So callback means that the function fit is going to call during the training our callback history, no? And after every batch finishes, it will do this thing. Okay. And then here we have some plots for you just to click and click. The convergence here. Here we have a plot similar to the ones that we saw in the slides. So I put here an exercise. Please try the whole data set. Go here to here and in batch, put the whole data set. Try a mini batch 100 if you want to try another value, and batch 1. So sort of to try to reproduce the plots that we have, and think, and afterwards we're going to discuss at 9:45. We're going to discuss why are the trajectories are different, and why the batch size equal 1 is slow compared to mini batch 200 or 1000. If you want if you want, you also can reply in Slack. Well, when you finish, put what you think it is on Slack. Otherwise, we are going to discuss at 9:45. Okay. Okay, we are back discussing. Thanks for your answers on the threads. So here I already ran it, and I can put the plot. So you should have got something like this. Here we see the loss decreasing with the steps, and here we see that the initial one, the red one, is random, and at the end we got a line that explains the data. Okay. And here, sorry. And here we see the trajectory, the same thing that we saw before. And then the questions, the reply to the questions, the answer to the questions is, well, first, why the trajectories are different. Well, the thing is that since every time for instance in this one we do batch size 100, every time when you evaluate in this batch size, the loss function is going to depend, is going to be constructed from this batch, this particular set of values that we got for the batch. If every time that you run a different batch, this value is going to the loss function is going to be slightly different. Okay, because the data is different. So then you get something that is oscillatory. If you use go to the extreme that all the data you use it to construct the batch is constructed from all the data set, then always the loss function is going to be the same thing. So you will see the continuous movement of the path. And if you go to the opposite side, to the batch size is only 1, this is the case where the loss function is going to be more different between one batch and the other one, because with only a single value. Then you get something very oscillatory. Then while you're approaching from 1 to the whole batch size, what happens is that as the batch size gets bigger, the data gets more homogeneous, and then the loss function is going to be more similar. So the oscillation is going to be smaller. Okay. And this one that was replied on Slack is exactly what Jonathan Vine said, that the batch size 1 does not leverage the vectorization. When you have a batch size 100 or 1,000, on the GPU, all these 1,000 evaluations for every item, for every sample in the batch can be run at one, concurrently vectorized, so all at the same time. But if you have batch 1, batch equal 1, then you have to evaluate 1, then the next one, then the next one, then the next one. So you cannot use vectorization. So here you run 100 or 1,000 at the same time, and here to run 100 or 1,000, it has to be one after the other one. Okay. So this is everything. Anyway, we are going to come back to this notebook later, because we are going to make it run in 2 nodes. Okay. So I'm going to move now to the slides and continue the. Oops. Okay. So we were here. So we saw all the different trajectories, and so every batch size is going to give you, in principle, can give you a different convergence rate. For instance, the stochastic gradient descent batch size equal 1. The convergence may be slower in some cases because it can move too much, but in other cases, batch size, if you use the whole training size, the path is very continuous, and if you don't use any mechanism to make it jump around, you may end up lost in local minima that are not good enough. And in general, what we do is to move between this case, so this case that is very continuous, to the case which is very chaotic with mini batches, to try to find the best, the fastest convergence. Okay, and this led us to why training with multiple GPUs. So the why is because the batch size is a parameter that you have to find the best value, and it can happen that while if you have a very large model, when you are studying which is the best batch size, you will arrive to the point that the batch size, the batch is not going to fit on the GPU memory. So in that case, well, there's nothing you can do except of adding more memory, and adding more memory is adding more GPUs. Then what you can do is to split the training into multiple nodes. So you get the batch that, let's say, batch size equals 64 fits on the GPU, but when you move to 128, then you get out of memory error. So what you do now is you select 2 GPUs and you put 64 in one GPU and 64 in the other GPU. Okay, and then we're going to learn now how the training happens like that. Okay, so just bear in mind that multiple nodes and multiple GPUs does not necessarily mean that you're going to go faster or that you're going to process more samples per unit of time. It can happen that you make it slow because distribution involves communication, and communication requires time. Okay, and then if you don't need it, if you don't need to distribute, then the best way is to do it in a single node. The same thing happens with the convergency. If your data, the best convergency that you found is with this example, for instance, 64 that fits on a single compute node, then if you add more GPUs and a bigger batch size, the convergence may be hard. We're going to see why later. But in this case, you just use single node. Okay, it's just a way of increasing your batch size. What we're going to do here. Of course, there are different ways of doing distributing the training. Another example here, we we split the data. No, this is called data parallelism. No? Another example could be model parallelism, which you split the model in different nodes, and every node or every GPU will compute part of the model and then put everything together. But this one is not, there is not a single library that does that. That is very complicated to do, and then I think you would need, I don't know, a case by case basis implementation. Okay. So we have data parallelism. We're going to split the data over multiple nodes. Okay. So in a single node, what we have is something like this. We have the data from storage. We read a batch. We pass it to the model. With this batch, we compute the forward and backpropagation. Then we get some gradients out of that. And with these gradients, we update the position of the weight. And we get another batch, and we repeat and repeat and repeat until we get convergence. Okay. Now, if we have, if we want to split the data, so to split the training, we get something like this. So we do in Daint, that would be like equivalent to do is run Python your script, and then we start 3 replicas of the model in 3 different GPUs, which in Daint is going to be 3 nodes. Okay, and the first thing that we do is the batch size that we were reading. We read a bigger batch and we split it in the different workers. Okay, so we get a big batch and we put 1/3 of the batch here, 1/3 here, and 1/3 here. Okay, so we do exactly the same thing. We do the forward pass. We get gradients, but at this point, when we get the gradient, since the data is different in every model, in every worker, we are going to get different values. So we need something else to synchronize and put together everything, so to complete the algorithm. And this is another step besides splitting the training, sorry, the batch. Another step, which is get all these gradients here, get an average gradient out of them, and put it back to every node, of course. So the update is done in every node exactly with the same gradient. Otherwise, all nodes are going to go to different places. No? So here, after we compute the gradients, then we get the same. We get the average. We put it back to all the nodes, and we get the same value of gradient to update the model. And now in this thing here, this setup that we have here, all the workers are going to do the same update, and the models are going to be identical while the training progresses. Okay. And another important point is that when you start the 3 replicas, okay, the initial state is going to be random. So this is going to be initialized random, this one too, and this one too, with different values. So at the beginning, when the training starts, besides this part, there is something that has to take the weights of one of the model and give it to the other models. So all of them start from the same position. We're going to get back to it. Okay. So this part here, the red part, is done in general in almost all of the implementations through the all reduce operation. So reduce is a name, it's an operation that comes from the MPI standard. Reduce, the reduce operation means getting one value, a single value, out of a collection of values. For instance, when you are in NumPy and you say, you have a NumPy array and you say x.sum, and you get the sum from it, this is a reduction. From an array, you got a scalar. This is a reduction operation. And the case that we're going to do is that we have many arrays, because every gradient is going to be an array of values, one value for every weight of the model. And then we're going to reduce it in the sense that from all these gradients, we're going to get at the end a single one. Okay, this is a reduction operation. And all reduce is defined in MPI as get all the gradients or all the arrays, do an operation to them that can be multiplication or sum or whatever you define, and give a single value out of this collection of arrays. In this case, what we are going to do is an average. So we get a single value and distribute it to all the nodes. So at the end, all the nodes, they have to have the same array. This is what MPI defines as or reduce operation. And or reduce, so MPI tells you this is what or reduce does. The implementation can be different from one version of MPI to the other one. The one we're going to use here, and it's again the popular, the common solution for this kind of algorithm in deep learning to train is called ring or reduce. So ring or reduce is again, of course, a variant of or reduce, and we're going to see here through a set of steps how it works. So the first thing of ring or reduce is consider this. You have 4 nodes. Okay, so you can have it for any kind of nodes, and every node has a different array. So let's say that we did the forward pass and the backpropagation, and at this point, after that, in the 4 nodes, since they were evaluated with different batches, they will have a different value of gradients, okay, which is an array. What we want is to get an average of all of them, and at the end have the same value, the same average value in all the nodes, so we can do the update of the model. Okay. So the first thing in ring or reduce is that the arrays are going to be deal with ring or reduce deal with the arrays divided by chunks. And how many chunks is the same number of nodes. So if you have here 4 nodes, 4 workers, we will have the array divided in 4 chunks. Okay, so this division is not in memory or anything. It's just a way of dealing with the array. So it's you will see now what chunk means. So it's going to be divided in 4 chunks, each of them. And the connections between the nodes, so because to communicate this array to do the average, is going to be in this way. Every node, so the node n, is going to connect to the node n minus 1 and to the node n plus 1 only. So, for instance, node worker 1, node 1, is going to connect to worker 0 and to worker 2, but it's not going to connect to worker 3. Same thing here. Worker 2 is going to connect to this 2, but not to worker 0. And then this way of connecting it is like it resembles a ring. No, you make a ring. There is no communication outside of this ring. And in this ring of communication, the data, the arrays are not going to be sent entirely. They are going to be sent only by chunks. So anytime there is data sent, it's going to be one of the chunks, never the whole array. Okay, so this is the main thing of the ring or reduce. Now let's see. We're going to see now how the algorithm operates. So it starts with so step 1. It starts with the chunk n is going to the worker n is going to send and sum the chunk n, the same index, to the worker n plus 1. For instance, here the worker 0 is going to send the chunk 0 to the worker 1, and we'll sum it. So here we have 65, 19, and it is summed here. Okay. Same thing will happen with the worker 1. The worker 1 is going to send the chunk 1 to the worker 2. Worker 2 chunk 2 to the worker 3, and so on. Okay, this is going to be the first step. So here, if you pay attention to the green moved to 1. So this is first step. Second step is the same, but now whatever was received in the previous step is going to be sent to the worker n+1. Okay. For instance, if we go to the initial step, a worker 0 received this brown chunk here, and then now in the next step it will send it to the worker 1. Same thing for worker 1. Worker 1 received the green chunk and it will send it to worker 2, and so on. And another step of that again. So whatever was received is going to be sent to the next worker, to the worker n+1, and so on. Okay. And now if we go back to the initial position, to the initial step, and we look to the green in the first step came here, in the second step came here, and in the third step it came here. And the same thing happened with all of the colors, with all of the chunks. So at this point, all the values are already computed, all the sums are already computed. Now they will be exactly the same, but only with send, because now there is no sum, it's just sending data. So everything that was received in the previous step is going to be sent again and again, 3 times more. And at this point, after these 6 steps, 3 sums and 3 sends, all the workers have the same array. Okay? So this is how the ring or reduce work. It's very simple. In general, in the general case for n workers, sorry, let me move one thing I have here from some. In the general case with n workers, there are 2 times n plus n-1 communications. n-1 are sums, and n-1 are the sends only. Okay. And a nice thing here of the ring or reduce is the total amount of data sent by each worker is independent, but virtually independent of the number of workers. Because if you look here, you have 2n-1, no? 2n-1 communications. And always the communication is the data sent is the array size divided n. So which is the number of workers. If n is large, n-1 divided n is pretty much 1. So for very large, it doesn't matter the size of the array, the total data sent is always is constant, and it depends on the array size only, which depends on the model, not on the number of nodes. Okay, this is something very good of the model, because other of the algorithm, because other implementation, if you wouldn't divide by n here, let's say that you do the same, you will have something n something communications multiplies times the array size. Then as you have more nodes, there will be more communication. We have to send more data, and this is bottleneck for sure. Okay. Now, before continuing, let's make a stop and look a bit where this thing happens on Piz Daint, which is the system we are interested in. Piz Daint, the communication is done through the Aries interconnect that is a network solution from Cray. And in particular in Aries, it has the dragonfly topology that it says how it's connected between each other. And the connection between the nodes is divided by something something called electrical groups. So electrical groups is 2 cabinets that has 384 nodes. And within an electrical group, all the communication is direct. Every node is connected to every node. There is no hardware in between except the 2 nodes. And now, when you want to communicate from nodes between different electrical groups, they pass by switches. It is organized kind of hierarchical, like a tree. Depending how far you at the nodes are, you have to cross more switches, and that can slow down. That could slow down because every switch has to handle much more communication than within a cabinet. Sorry, electrical group. So if you find that that's a bottleneck for you, or you suspect that the communication is a problem, you can use in your bash script this flag minus switches equal 1, that you will constrain your calculation to a single electrical group. But since it's constrained, you may end up waiting a bit longer for the location. Okay, you can find more information about all these things in the user portal. Okay. Small info. Okay, we go to Horovod. So this or reduce that we saw, we can do it. There are two main ways to do it. One with TensorFlow, natively does it, and Horovod, which is an external library. It's an open source library developed by Uber, and it not only works with TensorFlow, but it also works with PyTorch and MNIST. And within TensorFlow, works with different APIs of TensorFlow, and it's very general. And then, so we would like to start with Horovod because Horovod is more, compared to the native distribution of TensorFlow, Horovod is more transparent, and for the training pedagogically, I think it's better to start with Horovod because you can see you will do all the steps that you need. You will write it yourself, and it's easy to see to learn what we are doing. Okay. So Horovod, one of the best things is that it requires minimal code modification. In general, you always have to modify your code from a regular, if you have a regular single node of a program, to make it distributed. And we will see that it's 3 steps that we have to do only, 3 to make it distributed with Horovod. Horovod is written in C, is well written and optimized, use bandwidth optimal communication protocols, and it's very sophisticated. And a very good thing for Daint is that when we installed it, we found that it operates, it was very simple to set it up with Cray and Piz. We didn't have to do anything actually. But in our current installation, we use the NVIDIA Collective Communication Library that is called Nickel. And we'll see a bit about it later. And other good points are that it's actively developed, and it has a growing community. So you can, when you have problems, you can find GitHub issues and Stack Overflow. So everything that we need to write a program. Okay. The NVIDIA library communication that I mentioned before is there's a library for exactly what it says, for collective communication. Collective communication is a communication between multiple nodes. They have operations like or reduce, or gather, broadcast. And it's developed from NVIDIA to operate between NVIDIA GPUs. And again, it is sophisticated, and it's optimized to use high speed. And in Daint, yeah, it works pretty well with the Cray software, hardware. So let's see these 3 steps that I said that you need only to change Horovod. Sorry, to change to make it distributed with Horovod. Okay. The first thing is well, import the Horovod. If you use the Keras API, we do it like this, and we run Horovod init. That is to initialize the communication between all the nodes. And this is similar to if you have programmed in an MPI, it should be equivalent to do MPI init. Something like that. The next 2 things are the initial synchronization that I talked at the beginning, and the optimization. The initial synchronization, as I said before, is when you start the 2 replicas, the 2 models in the different GPUs or nodes. They will be initialized with random weights So in the loss function, they will start different places, and you don't want that. You want them starting all at the same place. So we have to do something to put them on the same initial position, so that both have the same weights at the beginning of the training. Okay. So this is the synchronization, and the optimization happens like this. So in the first step, the loss is gradients. The losses are evaluated and the gradients computed for different batches. So this one corresponds to batch 1 and batch 2. So those are the two workers. Remember the two workers are here. You get two different gradients. You do an average. This is I did it by hand. Maybe it will be shorter, but anyway. You get an average here, and you move with the average vector, and then you repeat. You get another two gradients, get the average, and so on. And this is how the optimization is going to happen. Okay, so there are different ways of doing this. The average. It's not this is not the only solution, because you have to, if you do a single node, you will for the batch. Let's go back for the batch 1 and the batch 2. You're not going to move this. If you do a single node for the same amount of data, you would get one gradient, and then you move here. Then you go to the next step, and then you move here. So you will get a different path if you do with the same data. If you do it in a single node, or if you do it in multiple nodes with this synchronous distributed algorithm. Okay, and that can change that can modify the convergence. Not necessarily we will make it worse, because otherwise we were not going to teach this. But it can be different. Okay, so you have to always pay attention and be aware that that it's not the same algorithm that you are running it in multiple nodes. You are changing the algorithm. Okay, and another solution, Horovod gives another solution that's called add assume, but it's not implemented in TensorFlow 2 yet. So we are not going to see it here. But you can find information. It's very simple. You can find information on the Horovod documentation. And instead of doing an average, it will do some sort of weighted average that, depending the spread of the vectors, if it's two vectors are to spread, it will give you something. I think a small movement, and if they are very close, if these two are almost parallel, it will do a larger movement. So to resemble more the single node situation. Okay. So okay, so this is the thing. The main takeout here is the two steps that we have to do: the initial synchronization and optimization, and always keep in mind that we're changing the algorithm. Okay. So this in code, this is done like this: the synchronization. Horovod brings something called broadcast global variables called callback, very long. That you run this only on the first step. No, this is only at the beginning to start from the initial position. That what you do is the weights of step 0, of rank 0 are going to be broadcasted to the rest of the ranks. So you will have, when you run this, all the nodes will have the same weights. And how you do it? So you run it like this. You create initial sync callback, and in fit, same as we saw first with the callback history, you pass it as a callback. Okay. Here, if you have a callback history, you put just comma and the callback history. You can pass all the callbacks. Okay. And the optimization is very simple too. When you do this, that we all know, you select the optimizer, TF-Keras optimizer. Then this optimizer, instead of passing to the model to compile it, you wrap it in Horovod's distributed optimizer. And then this is optimized that you will do. This one is the one that will take care of doing the average, okay? And that's it. This is the three things you have to do. And there is an extra step, which is not really part of the training, but it's if you want to save data, since you will have many nodes. If you save data, all the nodes are going to try to write it, and that can corrupt the data, can harm the file. But also you don't need it, because since the model is the same in all workers after every step, you just need to save your model or whatever you want to save from a single rank. So you can do if horovod.rank equals 0, and then you put there your save model or whatever you need to save. Okay. And that's it. This is the things that happens with needs to be done to distribute with Horovod. Here, this is some benchmark that we ran with the convolutional neural networks on ImageNet. So this is on Piz Daint. You see here that this is image per second. So this amount of image per second that I processed. And we went here from 1 to 512 nodes. This one is the ResNet 101, Inception 3, and VE16. The three are very famous models for computer vision. And you see here we go to very high values of image per second of throughput with Horovod and Nickel. And here you can see that this one, the scaling is a bit worse. Well, actually, it's much worse than these two. But when you see here, you have 100,000, more than 100,000, 100 million parameters compared with this one that has 23 and this one that has 44 millions. So this one in the communication, so is for the same amount of nodes, the communication is heavier. You know, it needs to send much more data. So the scaling is worse than these two. Okay, but anyway, it goes to very high values of throughput. Yeah. So this is well, it's another piece of what to do with Horovod. In Daint, we're not going to use it for the course because everything is going to be in Jupyter. But how it works, you do normal things here. You put the amount of nodes that you want. CPU per task, you can put 12. And then you load the module, load Horovod. The Horovod module has the version and has the version of TensorFlow at the end. So when you do this module load this, it will load the corresponding TensorFlow. In this case, it will be TensorFlow 2.2. So this is already everything is set up. You can export the OMP num threads for the OMP support. And we add these three environment variables that are for Nickel, no? Which is the backend for the communication. The first one is just for debug. It doesn't change anything, just prints more stuff. That is important. I think we like to have it because it gives some information in case something goes wrong. And these two is for the support of the network and the communication between GPUs. This is the name of the Crane network. If you forget to put these two, it won't work. So it won't tell you anything, but it will give you some strange state where it will be like a deadlock. Nothing is happening. There is nothing happening. You go to the GPUs, they're 100%, but the training is stopped. That it can be very confusing. If that happens to you, maybe you forgot to add these two things. Okay. And then this is the same as run Python, your script. That your script was modified to support to make it distributed with Horovod. Okay. Some additional considerations with distributed training is that the data must be split equally by workers to avoid load imbalance. So this is if for some reason one worker has to to process a larger batch or a more complex batch or something than the other ones, it will happen that some of the workers will finish and they will have to wait for the ones that are still working. And then at the end, in general, you're using, this is not really, you're not distributing, you are distributing one part and the rest is kind of being done sequentially, since you have one or two workers that are still working while the rest is still waiting. Okay, so what you want is to distribute all the load, so all of them operate at the same time, finish at the same time, and there is no node idle. Okay. You can do things like we're going to learn in the afternoon, like distribute your data set in many files and make some of these files to be read by particular nodes. So to avoid one file being read by many nodes at the same time. That one can give you speed up and, of course, avoid the I/O bottlenecks. So this is similar to the first one, besides harming the throughput and the performance. You can harm also the convergence if your data set is not well homogenized, but maybe this is true also for single node. And another thing is consider scaling the learning rate by the number of nodes that you have, of GPUs. But this one is goes in the same topic that I talked before with the ALASUM, with different ways of doing the average. This one you can try it, but it can be dangerous, because so the intuition behind it, if you go to the presentation on GitHub, I put some equations, but I'm going to skip that part here in the presentation now. The intuition about it is for the same amount of data, similar as before, you will get in single nodes, you will get many gradients, and you will update many times. If you have I don't know, let's say 64, you will get something like this for a single node, and then when you do 64 more, 64 more, 64 more, you will get another one, another update, so you will move some distance. Now, if you do that in multiple with multiple GPUs, this 64, 64, 64, 64, they're going to be run at the same time and given to update as an average. So if you get all this in the single node, you may with multiple nodes you will get all of them an average, and at the end you will move something very small. And then what you could do is to increase the learning rate, so the step is larger. But that can be harmful for the convergency sometimes, because if the gradients are too dispersed, that it can happen that a very long step is going to take a wrong direction. Okay, it's not going to be right, and so this is something to keep in mind. You can try scaling, but in general, you have to be careful. Okay. I think something like ALASUM that I mentioned before, when it's implemented, is going to be a better solution than scaling the learning rate. But this scaling the learning rate, you can find it if you go to the Horovod webpage. You can find this repeated many times. Okay. So now, just a small word, the TensorFlow equivalent thing to Horovod in natively implemented is through the module TF distributed. It's part of TensorFlow, and it fortunately, I don't know, I think this year they included support for computers like Piz Daint, which is a single GPU per node. So you use multiple nodes that work with the Slurm, and this one works in TensorFlow with something called multi-worker mirrored strategy and something called a Slurm closure resolver. With these two things, you will learn later with Enrique. that you can make it work without any external, without not Horovod distributed. Is to make it work distributed. Okay. So now after all this, we can we're going to play with what we learned. We go back to the notebook. So now it's the same notebook, but open the stochastic DSM 2 exercise that we are going. It's the same notebook, same thing as before, but it's set up as an exercise. So you do you add all the Horovod things. So we come here, exercise. So here I copy all the steps that were in the slides before. And what you have to do is to find comments like this one and replace it by the Horovod things. And then you have many things to do. This is very simple. It's just mostly copy and paste. Yeah. So it's just let me check the time before, because I think we have a break now. Ah no, the break is also perfect. The break is in 15 minutes. Okay. So perfect. So it's the same thing as before. You just make it work with Horovod and try different batch sizes and see what happens. At the end, you will get two plots, one for each node. And before you start, please, here we use IPC Magic, which is something from CSCS to support multi-node workload, let's say, in Jupyter. Go back to this. In Jupyter, so how it works is you start this notebook, this cell, sorry. It will take some time. You see here. And then the cluster is ready. Now, everything that you want to run on the cluster, this is a cluster with 2 nodes, you have to put it inside of this magic command. This is a magic cell, which means whatever is written here, don't run it on this notebook, run it on the IPy cluster, okay? So if here we imported socket, for instance, if we do now socket hostname outside of this magic, it will tell us that it's not defined, because everything that happens on the magic, it will be only valid on the cluster, not on the notebook. Okay, so here we run this get hostname, and we get the two, so the output for one node and the other for another node. Okay, same thing for the rest. So be careful if don't restart the kernel while the cluster is running. So in principle should be fine, but if you need to restart because you messed up or something, just come to the last cell and run here IP cluster stop, and then it will stop the cluster. If you run it again, you will see that it says it's not running, and then you can come back here to this one and start it again. Okay, now is what time is it? 33. I will give you until 40 to play with the notebook and do the exercise, finding the Horovod things, and then we discuss. One nice exercise is if you can run the notebook before without doing all the steps. So you have to do the init, but if you miss this one and you miss this one, you will get very strange results. And I think it's nice to have a look at what happens if you forget these two. So you see what is the importance of doing it before, just besides the fact that I already told you. Okay, so I'm going to stop here. Please let us know in the chat if you have questions or any problems. Okay. If you get the error that Hansel Gomez wrote, CUDA runtime implicit something, CUDA capable devices are busy or unavailable, just go to the previous notebook and restart the kernel and just keep running. Okay. This is that another notebook already booked the GPU. Okay, we are back, and I think we can discuss already the notebook. I will open the one Dataset solution. So here, the things that we have to do was first import Horovod, then initialize Horovod, initialize all the communication. For some of you that are interested, if this -- target 0 or target 1 will execute only in the node that you put, no? The worker that you put. So here we can check the version, not really relevant. So import initialize Horovod. And here, when we come here, so we generate the data. We generate the data. And here, pay attention, when we generate the data, we do ensamplers equal 1,000. So this cell here is going to be run in each node. So in every node, you will have different data. When you do random, this NP random is going to be a set of values in the first node and a set of values in a different node, in the second node. Sorry. So you have two different set of nodes of 1,000 each. Okay, it's not the same data. So here we create this dataset object, same as before from tensor slices. Now this dataset object is going to be different in each node. Okay. So in general, this is like we have our total training size is 2,000, and we're splitting 1,000 to one node and 1,000 to another node. Okay. So we do a shuffle in each node, the shuffle of the whole data. We select 100. It's 100 on each node. Okay, this thing is run on the two different nodes. 100 in a different node and 150 epochs. So the base size equal 100. Okay. We generate the node. We initialize the model on every node. So the two nodes have the same model, but with different initialization. So they have different weights. We have the same callback as before. So if they have different weights, we have to create the initial thing callback, and we use this thing here. That it means whatever is on the worker 0, whatever weights the worker 0 has, broadcasted to the rest of the workers. So they all have the same. And just pay attention that here just creates the callback. It doesn't run it. It's just created. And where you run it is here in callback initial sync history. Okay. So when in the feed, it will run in the first step, it will run the initial synchronization callback. So we have the two trains and the wait, I skipped a step, sorry. I skipped this step. The optimizer is, we use the one before, we pass it to the distributed optimizer of Horovod, and we create a new optimizer, and this is the one that we pass to compile. Okay? So we do the training. So this is fine, just we have to add the callback. And here in the plot, we get two plots. The convergence, the final values. So the final values should be the same. And here in this one, we get again two plots. And the path, let's see if I can fit them both in the, yeah. The two paths, they have to be exactly the same. If they are not the same, the two paths, it is that you forgot to add this guy here, okay? So they are the same in both nodes, and you see that there's something different here. That although they have the same shape, this one starts in this line and this one starts a bit after. So this is because remember that the loss function is created by summing over all the data set. Since the data set is different in each node, right? Because here we create the data, two different data in the same node, in the two different nodes. Then this value, this plot is going to be slightly different, okay? But it doesn't mean that the Horovod did two different things. It's just the plot that is slightly different, okay? And if we try the different batch sizes, you will see something similar to the plots we already saw for the linear model in a single node. And maybe I can show you quickly here what happens if you omit steps. So let's start. Maybe I can. No, I think I don't have anything running. I can start this. Okay, I think I had something already running in the other notebook. Yeah, exactly. Just a minute. Okay, I got my cluster. So we initialize. We generate the data, create the data set. Oops. Okay, if you have seen this error, some people already replied, but it's that another notebook is running is using the GPU. So you just come here, you go to the notebook that uses the GPU, do kernel, restart kernel, and that should do it. Run it again. Nope. So I can come here to this tab here and run leave only solution. Okay, now it works. You see here there is no other kernel running. I have a terminal, but the terminal is not a kernel. The model, and let's say that in the model we forget. No, let's start with this. Let's say that we forget to do the initial callback. So we don't put it here. So now the two workers are going to start from a different position, right? Different state. And now, and let's see what happens. So there is a training. We get already weird stuff. This plot, this one looks nice, but this one looks strange. And the final curves are different. So when we plot here, what we see is the same plot, the same shape, because the synchronization still happen, but they are two parallel curves starting from different place, going to I don't know, to any random place, because they start in different positions. So if you see something like this, which in general in your unless you're doing this particular example, this plot you don't see it, but this is what happens if you don't do the initial synchronization. Okay. So now if we do everything from the beginning again, and we do the initial synchronization, we should be able to see the right thing. So here, we start from, I wonder why this is different here. That's very interesting. But now you see that they both converged. But I think in this case, I don't know.
Hey, Rafa. I think you haven't started the first cells, so you haven't restarted it.
Yeah, it looks like it, right? Start here, restart the model. Okay, yeah, sorry, yeah, it's what Enrique said. Apparently, I didn't run one of the cells. Now everything should be fine. Okay, and now the other thing that so you know what happens now if you don't initialize. I hope this is illustrative. So if we start again, making sure that, and now they say that we forget to add this one. Or we don't forget it. We want to see what happens if you don't do the synchronization in every step. We do the training. Again, the training is going to happen because the training is done by TensorFlow. What's going to happen is that these things are different. You do two different trainings on two different nodes. So you really didn't do the distributed thing. So this thing can be, if for some reason you forget that or you call different the optimizer and you end up not doing the synchronization, you will get a training. It will be two different trainings. You're not going to be using the whole data set. You're just repeating the same thing twice. You see here that the trajectory is different. Okay. So now let me check the time. So there are questions. Okay, in any case, after the whole day, we have a Q&A session that if you have questions here or something come to your mind later, you just can ask it later, okay? So now, before moving to something else, let's come here and stop the cluster, okay, all of us, and restart the kernel. So now we're going to, okay. We're going to move to MNIST. So here in MNIST folder, there is MNIST, there are three things. Let's open the first two. I will go over them first. So we start with this one, 01 MNIST. It's the same thing as before, but just a more complex, more realistic model. We import TensorFlow. This is a single node. Create a model, compile it. Here we put the optimizer here, right? And then we get the data set from Keras dataset and next load data. So this is an NumPy arrays here. We do the same operation again. We use from tensor slices. We pass it, we convert it in to dataset, TensorFlow dataset. We shuffle and we batch, and we have now also a validation data set. We do exactly the same thing here. We do shuffle because we don't care, in this case, too much about the order of the validation. And so we fit. And now I can give you 5 minutes until 11:21 to convert this to Horovod. So it's the same exercise that you did before. Let's do it one more time. And this case, there are no plots or anything. It's just to run it again. Use you have as a reference the notebook 02 Horovod. You use import IPC magic, IP clusters, the same things as before. This should be a quick exercise, and just pay attention that after you do it in this setup that we did here for the validation and the training, the validation loss and accuracy has to be the same for at every state for each worker. Okay. So I give you until 21. Okay, we are back. So here we start the cluster. Again, the same thing as before, import Horovod. Here we take the optimizer from here and we create this optimizer object here and wrap it by the Horovod one. Create the callback and pass it in the training. And there is an extra step that I didn't mention before, that is dividing the data in different workers, which is this one here that I have marked. So before, when we generated the data, we did X and Y equal random in 2 different workers. So we already we generated the data different in all workers, so it was fine. We didn't need to split the data because it was already split since the beginning. But now here, when we do TF load MNIST, it will load MNIST on X and Y on both nodes, the same data, of course, because it's the same data set. It's not a random values. So in this case, if we don't do this, we're going to be sending the same data to both workers and do it exactly the same training. We're not achieving anything. So here, what we have to do is this simple line. So to the data set operations, we add chart. Chart is divided in pieces. You pass the total number of ranks, Horovod.size, and the Horovod rank. This is the current rank. So here, if we print here, execute this in a node, in both nodes. What? So okay, sorry, if we execute this in both nodes, we get 2, the size, and for one node this is going to be 0, and for the other one is going to be 1. So this is going to do that when you're fetching batches, one batch is going to go to the worker 0 and one batch to the worker 1, and consecutively like this. And like this, you are going to be splitting. So here you will have 128, same as before, going to rank 0, and 128 working going to rank one, and in total your full batch processed is going to be 256. Okay, only with this line. So we don't do it on the validation in this case, because we want, for this example, to check to do the validation the same, to test in both nodes the same validation data, so we can make sure that we did everything right. So if we come here, so this is the training, the values, they are not the same. They are slightly different for each node, but the validation is exactly the same. You see, validation loss and accuracy is the same at every step for each node, because the state of the node is always the same. Okay, and that's it. This is the only thing we have to add. And I did something here with the CUDA devices apparently, but I want to make a point that Enrique told me that in the presentation I said something that it was wrong, which is I said that the algorithm is different, but what I meant is that if you consider if you process so let's say that here 128 and 128 consecutively in a single node, you do 2 batches, so you update twice. Okay, and if you process this 256 on 2 nodes, you're going to get 2 gradients and average and do a single update. So this is the thing that I meant it was different. Of course, if you run 256 in a single node with a single update in a single batch, and the same thing in 2 nodes, is the same result. It's the same. Just what is different is processing the same amount of data sequentially with different updates, or at the same time in a multiple nodes with a single update. Okay, sorry about the confusion before. So now let's see if there are questions. Okay, Vladimir, I'll get back to you offline. Now I pass the microphone to Enrique, that will teach you the same thing, but now how to work it with TensorFlow native distribution implementation. Okay.
Hi guys, let's just share my presentation. Here you go. So can you see it? I think it's cropping a little bit, but it should be fine. So, so basically, thanks Rafael for this awesome introduction. And he explained really well, I think, how Horovod does all the distribution. And we've been using Horovod, the CSCS, for quite a while, and it's a very stable product. But I would say, yeah, it's quite recent that TF supports the multi-work strategy natively as well. So you actually can do the same thing without using Horovod at all. And I'll show you just briefly how it works. Basically, TF introduced a distributed strategy that's called TF distributed strategy. And it can create a scope within it, and where it wraps your model and makes an abstraction that you basically use the model as you would be like a single node model, but it's actually doing the distribution transparently for you. So if you do that, and if you have a single node and multiple GPUs, that's very simple. It was supported since, I think it's like support in TensorFlow 1 already. So you can do the TF distributed mirror strategy, like in the example here below. You instantiate the strategy, and then you create this strategy scope. And then if you declare and compile your Keras model, or actually TensorFlow model within this scope, everything that happens after this is gonna be transparently distributed. So basically the user doesn't have to do anything with the dataset or with the model anymore, and it will automatically distribute across all the GPUs that you have. But this just remind, this is for a single node worker, right? So this works really well, but only if you have a single machine with lots of GPUs. For example, on AWS, you can have, I think, 8 GPUs on a single node. If you have your own rack, you could have like easily 4 GPUs in the same node. And then by just doing that, you can already use all your GPUs, no problem, right? These automatically use nickel all reduce as well, as you just saw before. The same all reduce algorithm synchronized across the GPUs. And it also does data sharding automatically in your dataset. Although you have done nothing on your dataset, it automatically will shard parts of the dataset to different GPUs, right? But as I said, this only works for a single node. And at CSCS, our nodes only have a single GPU, so it's completely useless for us. But it's good to know anyways. But then there is also a strategy for multi-worker, right, that we're going to see now. And that adds a bit of complexity, as we saw before. You have network communication between the nodes, and they're actually running different processes. They're running different operational systems. And we facilitate it inside CSS and JupyterLab using the IPC magic, as you saw. But it's not a default thing. So if you go to another environment, you might not see the IPAL parallel set up in that way already. You could do it yourself, obviously, but yeah, that makes it much easier. So generally, when you do multi-node distribution, the easiest way to do is running a separate script on each node and then do the synchronization as it is, right? Not on JupyterLab. As I was saying, so then we have now this multi-worker mirror strategy. And it's still more or less an experimental stage. It works pretty well, but they still kept in the experimental namespace for now because it has a few things they keep changing. And hopefully in the next versions, it will be stable and go back to the normal distribute namespace. Sorry. So as we say, these also use the Nico all reduce, as you saw, and same ring algorithm all reduce for all gathering. So all the gradient distribution is done the same way you just saw in Horovod. And it introduced a few interesting things. So it has a fault tolerance mechanism using a Keras backup and restore callback. And as I said, also like in the mirror strategy, it does the sharding automatically, right? So you'd not have to do the dataset.shard that we just saw. So this might get a bit confusing for you guys that if you just introduced the other framework, but it's just interesting that you should know that there is the native as well. And we'll see more in details tomorrow specifically. We're gonna work with a few examples. Maybe using both if we have time, then you can see the advantage and the disadvantage of each other. Anyways, going back to this strategy, the multi-worker mirror strategy, it expects a configuration where you have to give each node separately, which is kind of annoying, right? But this is how it used to be for very long. And some of the TensorFlow strategies still use the tfconfig a lot. But in Slurm, in our workload manager that we have at CSCS, also actually, you already have all the information that you need here, the sockets and the ports and everything. or in the environment variables. And in TensorFlow 2.2, they finally fixed the cluster resolver that requires the same information that we saw on the environment variable, but it can automatically queries all of them. So it could overwrite them, but basically by just instantiating the thing, you get all of that automatically, right? So at the end, you basically just have to instantiate your multi-worker mirror strategy and then give it a Slurm cluster resolver. And you don't need to give any parameters, and it's gonna get everything for you. I specify here the communication as Nico, but it has an automatic as well that would work. And then as I'm using here the IPC cluster magic, these will run in all nodes as we saw before. And if I invoke my model in this strategy scope, when I do model fit, it would just magically distribute across all the nodes. Some people might not like this because you actually don't see what's happening, and it's quite hard to understand what is going on everywhere. You can profile your model and see more or less what's happening, but as you saw in Horovod, it's a bit more clear what's happening in each step, so that's why we choose to keep it as well. But yeah, we have this alternative now, at least. Have a question? Yeah, just as a quick recap. So the sharding, differently than Horovod, happens automatically. And it also does sharding on the validation, which you see later on. So, well, and it can also use file sharding, right? So if, as we're gonna see TF records later on, maybe I'm not gonna get into too much details, but you could parallelize the opening of the files as well. We see more details. As I said, the fault tolerance part is quite interesting. So if you add this backup and restore backup callback to your model, if any of the nodes dies for whatever reason, it will save a checkpoint on every epoch. And if you just restart your job after that, you can restart from where it stopped. So it's very handy if you don't want to lose all the compute time they use. The annoying thing, it doesn't support model predict at all. So you cannot run model predict when you're using the multi-work strategy. So you basically have to save the model and open in a single node instead. In Horovod, you have more control to do whatever you want. So yeah, let's go to the to your notebook. I'll have to change my share. All right. So yeah, if you open, sorry, let me show where it is. So in stochastic gradient descent again, and then if you go to MNIST, well, I guess you already there, yeah. If you open the MNIST TF distribute here, we have a simple example on how to use this new abstraction. So yeah, just to make it clear again, we're going to be using the PX magic, and every time we do not use it, this runs in a single node, right? So you have a single output when you start your cluster. So I'm going to have the 2 GPUs here, but every time I use the magic, this runs in the 2 machines, right? So I get 2 outputs, 1 for each. And printing the same stuff that Rafael was showing before, we have the 2 host names, and each one has a GPU, right? Just to be clear. And I'm not gonna get you guys to do this yourselves right now because it's quite simple. Let's just go through it. So basically you have to instantiate your strategy as we were saying before, and that's it. You could choose to still use the old TF config, which would be basically like that. If you by just instantiating your TF config, that would work as well. But yeah, it's much easier. Sorry. It's much easier to just use the Slum cluster resolver. Right. Here I'm grabbing the number of workers in the node ID, just as we did in Horovod, but you actually don't really need to know, like, the TensorFlow API try to abstract the distribution completely from the user. So you don't even need to know that you're running in several nodes. But you might actually want to scale your learning rate. And one thing that's a bit non-intuitive in this paradigm is that you have to scale your batch size as well. So this is different than in Horovod. In Horovod, if your batch per worker was 128, you had 128 on each machine. But now, if you use this the distributed strategy, you actually need to specify the global batch size, right? So if you have 10 machines, you need to give it 1,280 because you will split the batch later on. And so that's the only thing. I use the number of workers to multiply the batch size and the learning rate, because as I have less noise on the batch, as less sample noise on the inside the batch, I can allow myself to have a larger learning rate, right? Then we define our data set. Now, as we saw, you can shuffle. I delete this. But here you see, we're not going to put any sharding anywhere. Just remind that the batch size has to be scaled by the number of nodes, right? And that's it. So you have a regular batch size. I'm not going to do anything with that. And then when I run model fit, these will work magically, basically. Let's just check the data set quickly. And so if you see, if I get the validation data set here, and just take one example of it, it's going to give me the full batch size. So 256, let's just go back up here. And remember, I had 128 multiplied by 2. So my batch size will be actually 256. And when I do take one from the validation data set, it's actually going to give me the full global batch size. It could be that this doesn't even fit in the GPU memory when you're doing the training, but it still shows that, right? And if I show both the output of both nodes, you see that I have exactly the same batch on both nodes, right? So I have the same image here and the same labels. And this is very weird for the user perspective because you don't actually see the sharding at all, right? But you have this method and this strategy. It's called distributed dataset, which is called automatically by Keras. So you do not have to call this by hand normally. But I just want to show that after you actually call it and you do the same print and plot here, I have actually just half of the batch size. And the batches are actually different now, right? So it's sharding the batch itself automatically. If that's not super clear right now, you're going to see more examples later on. I think Raphael is going to show the input pipelines. So, but yeah, basically, the user doesn't need to know anything about the distribution. That's the idea, right? It has to be completely transparent. So when you do the steps per epoch, that you have to give it to fit model, you're actually gonna give the size with the full batch size, the global batch size. All right, so let's define our model, which is very it's very similar to the model you had before. I just add the batch normalization here. By the way, how many of you guys are familiar with batch normalization? I'll put it in Slack actually. Have you used So yeah, it's a very simple perspective, right? But we see what happens when you distribute batch norm later on, right? So it's a very simple model with cross entropy loss and stochastic gradient descent optimizer. And as I said before, all you have to do is to wrap your model within this strategy scope. It doesn't actually need to be a function, right? You create a function here just to make it simpler. You could actually put this whole scope up here instead of the function. That would also work, right? I would have to rename everything below, but yeah, well, yeah, and we use the return. But let's leave it as it is. But that's it. That's all you need to do. And after that, you can call fit, and it will distribute your whole work. Yeah, the main difference with Horovod here is that it would also distribute the shard the validation. So only half of the validation is actually being used on each one of the nodes, but it also averages the results after. So you also don't see anything. So if everything goes well, you shouldn't see anything from the distribution at all on your training pipeline. Which some people might like it, some people might not really like it, what happens. But as I was saying before, we had this batch normalization layers now that we didn't have before. And if you think on the whole paradigm of the distribution, what we're doing before was to calculate the gradients and then distribute the gradients, right? Synchronize the gradients across all nodes and then update the model. But as you may know, the batch normalization actually gathers statistics from the inputs during the forward pass as well. It runs a moving average of all the inputs of that layer. And these statistics actually not necessarily synchronized by what you see. So after we run the fit, if you run the fit yourself, you will see that every weight of the model is the same everywhere. But if you check the batch normalization layer, you might end up seeing that there's small discrepancies inside the weights. So here, basically, I get our model and get the first batch normalization, and I'm just printing the first 10 parameters of that layer, right? From the moving mean, which is one of the statistics that it gathers, right, together with the variance. And you see the values are similar, but they're not the same. And is that a problem? It's not a massive problem because it's actually on the 5th decimal in this case, but it could be a problem if you have a very small batch size per node. If we go back to the slide, so yeah, so ideally we should actually synchronize our statistics as well. So just a quick refresh, the moving average from the batch norm are basically the mean of the input of that layer and the standard deviation. Sorry, the variance actually, it's actually calculated. So for each batch, it's going to calculate the mean and the variance of that batch and keep those statistics. And then it's going to average, run a moving average, exponential moving average of those statistics across the train. But this all happens in the forward pass, and it's not going to get synchronized by the distribution strategy. What does get synchronized is the gamma and the beta parameters. There are 3 parameters from the layer itself. So their gradients are going to be synchronized. To solve that issue, they introduced this special layer. It's called sync batch norm, which is very simple actually. It's just a different method to calculate the 2 exponential moving averages. And after it calculates it, we can actually look at the code and see the time. Yeah. So if you open the documentation and then go to the code of the thing, which is a good habit, I think. So you see there's a lot of comments here on GitHub, but then let's just zoom in a bit.
We're still seeing the slides, Enrique.
Oh, thank you. So, yeah. So if I go to the documentation, can you see the page now, right?
Yes.
Thank you. So if I go to documentation, it's the same documentation as the normal batch norm, and I'll go to the GitHub link of it. And there's a bunch of documentation, as we're saying. But down here, it actually just boils down to a single method, which is calculate mean bar. And all it does really is calculate the simple mean and variance of the batch, but then it runs these reduced sums for both of them, which synchronizes your weights in real time. So, and well, there is a bunch of calculation here, but it's actually very simple math. If you have time to have a look after, it's quite interesting. Sorry, I pointed to the wrong methods. This is just the TF, the all reduces down here. Sorry. So if you want to go ahead and you can change your batch norm here for the experimental sync batch norm, and you see that after your training, then your weights should be the same. So how much time do we have? Yeah, I guess it can give you guys a few minutes to do that. Just lines. Oops. Yeah. So basically, just replace the layer with the sync batch norm, and you see that it should actually be smoothly now and have the same weights on both sides. So yeah, someone was asking if you can do that on Horovod as well. And yes, there is a similar layer implemented in the Horovod repository that you can replace your model, and we'll do exactly the same. So could everyone run the model? Anyone have any problems? If you did, please let us know. But yeah, basically it's very simple. Just replace the layer, and if you train it at the end, you should have exactly the same weights, right? Obviously, if you check any of the other layers, they have to be exactly the same. So the idea with both frameworks as well is that you should have exactly the same result as if you would be running on a huge GPU with all the possible memory and compute, right? Obviously, there is a little trade-off, as we saw before, because of the synchronization of all the models. Certainly, synchronize the batch norm also introduce some latency, because we have to synchronize it also during the forward pass. But because the batch normalization layers are pretty small, they only have a few thousand parameters normally, right? Normally you only have to synchronize 2 parameters per channel, even on really large CNNs or whatever you're training. This shouldn't introduce much of a delay if your network is reasonable. And yeah, it's much less than the gradients for sure. So basically, that was what I wanted to show you guys right now. We're gonna play a lot more with both strategies later today and tomorrow as well. So, but yeah, if you have any doubts, please let us know. If you prefer to verbalize your question, you can also, I don't know if you can raise your hand here. I think you can, right? but we can unmute you and you can give us a shout. Or just type your question in Slack and we're going to try to answer it. Let's see. So yeah, we'll have our lunch break now for 1.5 hours. Right. So I guess we get back to you guys then. There's a question maybe. What about distributing training on CPU only nodes? So you're talking about multiple nodes, I assume. I haven't really tried, to be honest, but I think it should work the same. It doesn't really imply that you need GPUs. So if you use the same thing that we just did before, both with Horovod and TF-DIST, it should work. I'm pretty sure. But yeah, as I say, I don't think I ever tried to distribute only CPUs. CPUs generally are very slow for deep learning, like really, really slow. So unless you have thousands of them, you wouldn't really distribute deep learning on CPUs. It would be very wasteful. Like you'd be running a lot of CPU hours to train a small model. People used to do that in the past, but yeah, it's not a great thing to do. Is any other questions? We got 30 seconds. Someone's typing.
If there are no further questions, I suggest we close the video stream. People can still use Slack if they have questions meanwhile, and then we reopen the webinar at 1:30. How about that?
Cool. Buon appetito.